Hello and welcome. This is Matthew. And today is supposed to be day 3 of the Advent Calendar Integral Series. Now, like I said in the last video, I didn't forget, I just didn't upload day 3 through day 8. Now, today is December 9th, and you'll be getting all the videos, including um, day 9 of the Integral Series. Okay, and the first day back, I thought, why not do a hard integral? A generalized integral, in this case. Now, what is n? Well, n is a constant. And I want to take n to be an element of the positive real numbers, implying that n is greater than 0. There we go. That is n. Okay, cool. The second thing I would like to do is to notice we have a natural log function. And I would like to define a function, I of alpha, as the integral from 0 to infinity of e to the negative x to the n divided by x to the n plus 1 times x to the alpha dx. Now, this doesn't really look similar to I, but if we differentiate both sides, I prime of alpha, this is of course going to be the derivative with respect to the parameter alpha of this integral right here. Okay. All right. And due to the special case of Leibniz rule for differentiating under the integral sign, and that special case is we don't have functions of alpha in our limits, we can go ahead and just bring in this derivative, but instead of being a regular derivative, it's going to be a partial derivative. So that means that I prime of alpha is going to be the integral from 0 to infinity of e to the negative x to the n divided by x to the n plus 1, and then the partial derivative of x to the alpha dx. Now, this derivative is very easy. This derivative is going to evaluate to x to the alpha times ln of x. All right, there we are. So if we replace this in our integrand, okay, there we are. We have this. Now, this looks very, very similar to our integral I, doesn't it? Well, if we set alpha to be equal to 0, so that means I prime of 0, where alpha equals 0, this is, in fact, going to be integral I. Of course, if you can't see that, we're going to have a 0 here, and this is just going to collapse to 1, and there we go. That is exactly our integral I. Cool. All right. Now, instead of focusing on I prime of 0, which is our integral, let's focus on I of alpha, our function. That has not been differentiated. So let's go ahead and remove all of this. Now, all I did here was show the relationship between I prime of 0 and I, so I can go ahead and delete it. All right. Now that we're focusing on I of alpha, the first thing I'd like to do to I of alpha is have a e to the positive 1 and then e to the negative 1 in the numerator. Of course, these will cancel and just go to 1. But instead of, having both of them in the numerator and then they just cancel, I'm going to take out the e to the positive 1 outside of the integral. So that means I of alpha is going to be e times, I'll show why this makes sense in a second, or why this is needed in a second. e times the integral from 0 to infinity of e to the negative x to the n times e to the negative 1 divided by x to the n plus 1, and then x to the alpha dx. What I want to do is combine the exponents of e and then factor out a negative 1. There we go. So now we'll have I of alpha is equal to e times the integral from 0 to infinity of this integrand right here. Cool. Now, before we go any further, I'd like to define another function. Now, I know, 2 functions in one video, it's crazy, right? But it's just the solution I came up with to this integral. Now, I'd like to define the function f of t as the integral from 0 to infinity of e to the negative t times x to the n plus 1 divided by x to the n plus 1 and then x to the alpha dx. Now we can observe something. If we let t equal 1, so 1, 1, and then multiply both sides by e, this is exactly I of alpha. Okay. But instead of focusing on I of alpha, I want to focus on f of t. There we are. Okay. Now, get ready, because we are going to differentiate again. We're going to differentiate with respect to the parameter alpha. Man, I speak way too fast. I need to slow down. Jinkies, man. I really need to slow down. I speak way too fast. Okay. So like I said before, we want to differentiate with respect to the parameter t. And, of course, we're going to have derivative with respect to t of this integral, and I don't want to write it out again, so we are just going to copy and paste. There we go. Now, like I said before, this is the special case for Leibniz rule of differentiating under the integral sign, where we don't have functions of t in our limits. So we can go ahead and just bring in this derivative, and instead of being a regular derivative, we're going to have a partial derivative, which means we're treating every other variable except t as a constant. All right. So that means f prime of t is going to be the integral from 0 to infinity. I will bring out the x term, so x to the alpha divided by x to the n plus 1 times the partial derivative with respect to t of then e to the negative t times x to the n plus 1 and then dx. Okay. Now, this derivative is also really easy. We're just treating every other variable like constant, so we're treating x like a constant as well, because it's just a partial derivative. Okay. And like I had just said, this derivative is easy. I'll leave it as homework for the details of evaluation, but if you do it properly, you'll have negative times x to the n plus 1 times e to the negative t times x to the n plus 1. Now, let's replace this with inside of our integrand. Okay. Now, this looks a bit weird. Let me go ahead and move this over. And then put parentheses. There we go. And of course, this term and this term will cancel, and we'll have a negative sign outside. So now we have f prime of t is going to be negative the integral from 0 to infinity of x to the alpha times e to the negative t x to the n, and then minus t. Now all I did was multiply out this negative t into the x to the n, and then the 1. Okay, and now we can just separate this into two different exponential functions, because we can just, combine them again, and there we go. So we'll have an e to the negative t dx. And since t is just a constant in this case, we can just go ahead and bring out this e to the negative t outside. So now we have f prime of t is going to be negative e to the negative t times the integral from 0 to infinity of e to the negative t times x to the n times x to the alpha dx. There we go. It is now U substitution time. Absolutely. Yes, U substitution. Let's do it. Alright. Now, let's take U to be equal to t times x to the n. This means that x to the n is going to be u over t, or x is equal to t to the negative 1 over n, and then u to the 1 over n. Now let's differentiate both sides to find our differential element. We have dx is going to be t to the negative 1 over n divided by n times u to the 1 over n minus 1 du. Now, as for our limits, we have when x goes to infinity. Now, like I said before, n is greater than 0. This means that u will also go to infinity. And as x goes to 0, u will also go to 0. Okay. So, this means that f prime of t is going to be negative e to the negative t times t to the negative 1 over n divided by n. Now, another thing, we notice we have an x to the alpha term right here. And we recall that x is equal to this guy. So now we just need to raise both of them to the power of alpha. And then we'll have a negative alpha here and just a positive alpha there. And since t is a constant, we can bring it out. So we'll have another t to the negative alpha over n times the integral from 0 to infinity of e to the negative u times u to the 1 over n minus 1 times u to the alpha over n. Now this term comes from the x to the alpha term. And then du, of course. Alright. Now let's combine these exponents right here. So we'll have a negative 1 over n times 1 plus alpha. Yep, that's correct. And then this one will be a 1 over n times 1 plus alpha, and then minus 1. There we go. Okay. Now, what does this integral right here evaluate to? Well, it evaluates to gamma of 1 over n times 1 plus alpha. Now, why is that? Well, if we replace this term with, say, maybe q, this is just going to be our Euler gamma function. And like I said before, or like we had before, and I didn't say this, like we had before, if we take q to be 1 over n times 1 plus alpha, we'll have the integral that we just had right here. So there we go. So all this implies, I need some room, we'll go down here, that f prime of t is going to be negative e to the negative t times t to the negative 1 over n divided by n, of course, times alpha plus 1 up here. Let me make sure everything is correct. Yes, and then times gamma of 1 over n times alpha plus 1. There we go. And now we have f prime of t. Okay. Now we need to observe something. Let's go all the way up here. I of alpha is just going to be e times f of 1. Okay? Now why is that? Well, if we plug in 1 here, we'll have f of 1 is going to be this integral. And if we multiply both sides by e, we're just going to have I of alpha. Cool, right? All right. Now that we have a relationship between I of alpha and f of t, we need to apply this to f prime of t. And by doing that, we need to first find f of t. So how do we do that? Well, we need to integrate both sides. Cool. But also, since I of alpha is going to be e times f of 1, this is also going to be the integral from infinity to 1 of f of t dt times e. Now, why is that? Well, hold on. Prime, right there. Now, why is that? Well, this is just going to be e times f of 1. Now, like I said before, I apologize for not having that prime there. I fixed my mistake, though. Minus the limit as t goes to infinity of f of t. And if we go all the way back up to f of t, right here, and if we take the limit as this goes to infinity, of course, we're going to have like a negative infinity right here. Of course, we can't just put up infinity right here because infinity isn't really a number, but just imagine we're taking the limit. This is going to be the same thing as 1 over technically e to the, infinity, or the limit as x goes to infinity, or I mean, not x, t. So the limit, we'll put L, and we'll put infinity, t goes to, right here, which this will just collapse to 0. Now, hopefully this makes sense. I'll write it over here to make more sense. Okay. The limit, as t goes to infinity, of f of t is going to be the integral from 0 to infinity of the limit of t goes to infinity of 1 over e to the t times x to the n plus 1 divided by x to the n plus 1 times x to the alpha dx. And this limit right here is just going to collapse to 0. Therefore, the whole integral, the limit as t goes to infinity of f of t, is going to be 0. Now, hopefully this made sense. I know I kind of started off not really making any sense, but hopefully what I just did right here made a little bit more sense. So, let's go all the way back down here. This limit, like I just said, is going to be 0. So, we'll just have minus 0, or basically nothing, and then there we go. And remember what I said before, this is going to be I of alpha. Therefore, I of alpha is going to be e times the integral from infinity to 1 of f prime of t, and then dt. Or we can go ahead and multiply a negative sign and start from 1 and go to infinity, because this is just going to be negative e times the limit that I just did a minute ago, minus f of 1, okay? And this negative are going to cancel. Therefore, I of alpha is also the same thing as e times the integral from 1 to infinity of f prime of t dt, and then a negative sign right there. Now, like I said, hopefully I am making sense, or hopefully you understood what I just did. But yeah, there we go. I of alpha is equal to negative e times the integral from 1 to infinity of f prime of t dt. Okay, and if we go up here, we already know what f prime of t is equal to. It's equal to this guy. And since we don't see a t inside of this gamma function, we can just bring it outside of the integral. Therefore, I of alpha is going to be negative e times gamma of 1 over n times alpha plus 1. I am, in fact, running out of room over here. Let me move this over. Okay. Times the integral from 1 to infinity of negative e to the negative t times t to the negative 1 over n plus 1, and then divided by n, then dt. And we could also bring out this 1 over n out here. Also, this negative sign and this negative sign will cancel, and here we are. Okay. Now, in the exponent of t, we can just go ahead and add 1 and then subtract 1. Okay? Now, this is the same thing as saying minus n inside. We can bring it in, and then, of course, minus 1. And then we can go ahead and bring in this negative, and then we'll have n minus alpha minus 1. There we go. Now, this is the exact same thing to what we had before in the exponent of t. Okay. Now, this integral looks very similar to the incomplete gamma function. Now, the incomplete gamma function is going to be gamma of a comma z, and this is going to be equal to the integral from z to infinity of e to the negative t times t to the a minus 1 dt. And if we let z equal 1, and then a equal this guy, so let me go ahead and give myself some room. Gamma of what exactly? N minus alpha minus 1 over what? N. Okay, n. There we go. I need some more room. 1 over n times n minus alpha minus 1, and then minus 1, and dt. We have identical integrals. There we go. So, that means this integral right here is just going to be the incomplete gamma function of n minus alpha minus 1 all over n, comma, 1. There we go. So, this means that I of alpha is going to be e over n. Now, let me see. Yes, e over n times gamma of 1 over n times alpha plus 1 times the incomplete gamma function of 1 over n times n minus alpha minus 1. No, comma 1, and there we go. Now recall what I had said before. I prime of 0 is I. Whew, now we are really getting close to the end result. This is getting very, very exciting. But before we get there, we need to differentiate I of alpha and then set alpha equal to 0, which is a handful. Okay. It's a bit hard, but it's not as hard as you might think. Okay. So, we need to differentiate this guy right here. Now, of course, we can just go ahead and take this out of the derivative. So, I prime of alpha is going to be e over n times the derivative d alpha right there of this guy. Copy and paste. Perfect. Okay. Alright. Here we are. Now, we need the product rule and the chain rule for this derivative. Okay. Now, remember what I said before, n is just a constant, so we will not be really needing a partial derivative since n is just some number greater than 0, and it's an element of the positive real numbers. Okay. So the product rule, we need to take the derivative of this guy times this, plus the derivative of this guy times this. That is the product rule, and also we will need the chain rule as well. So, we'll have e over n, of course, it's right here, times the derivative of this guy times this. And the derivative of this guy is going to be gamma prime of 1 over n times alpha plus 1, and then times the, we need the chain rule, so times the derivative of the inside. So then times 1 over n. That's going to be the derivative with respect to the alpha inside of the gamma prime of this guy. Okay, so that's what we have. We needed the chain rule, and after performing the chain rule, we have the derivative of this guy is equal to this. Now I hope this is making sense. So let's bring this out over here. Okay. And like I said before, product rule times this guy. Gamma of 1 over n time of n minus alpha minus 1, and then comma 1. Okay. Now, plus this guy times the derivative of this. Okay. So plus gamma of 1 over n of alpha plus 1, and then times the derivative of this guy. Now, before we continue, the derivative, I guess partial derivative in this case, of a, of the incomplete gamma function, this is going to be equal to the Meyer g function, 3 right here, 0, 2, and 3, and then z, and we'll have a 1, comma 1 up here, and a 0, comma 0, comma a. And then we'll add ln of z times the incomplete gamma function of a, comma z again. There we go. So this is the derivative of the incomplete gamma function with respect to a. Okay, now if we let z equal 1, in this case, because over here we have a 1 inside of our incomplete gamma function, where z is supposed to be. So we'll plug 1 there, and then 1 here, and then 1 here. But ln of 1 is just going to be 0. Therefore, we can just get rid of this term. And the derivative of the incomplete gamma function of a comma 1 with respect to a is going to be the Meyer g function, and we'll have 3 here, 0 here, 2 here, and 3 here. Now, of course, this means that m is equal to 3, n is equal to 0, p is equal to 2, and q is equal to 3. That's what these numbers are right here. This is m, this is n. Well, we'll have a lowercase n in this case, so I don't get confused with this n over here. This is p, and this is q. That looks like a 9. Still kind of looks like a 9, but oh well. All right. Cool. Now, we also will need the chain rule for the derivative of this incomplete gamma function, because we don't just have an a here. We have this term right here, and we are, in fact, differentiating with respect to alpha. So, let's go ahead and move this over. We'll have a gamma, and we'll have a 1 over n times n. I need a little bit more room. Gamma of 1 over n times n minus alpha minus 1. There we go. And the derivative with respect to alpha. I guess we really don't need the partial anymore. And alpha. Okay. Now, instead of just a over here, we'll have a 1 over n times n minus alpha minus 1. Of course. Now let's space this out a little bit more. Okay. And we need the chain rule, so we need to take the derivative inside of here, which is just going to be a negative 1 over n, so times a negative 1 over n because of the chain rule. There we go. And we can just take the negative over here. Actually, we can just take the negative 1 over n over here. Cool. Now, I hope this made sense. Okay, so now we're going to have to multiply by negative 1 over n, and I will copy and paste the Meyer g function. Copy and paste. Okay. And we can go ahead and take this negative 1 outside, so we'll have a negative there. And we also see a 1 over n and a 1 over n here, so we can factor it out completely, times 1 over n there. And then we'll have an e divided by n times n, or n squared on the outside. Cool. Okay. Now, this is I prime of alpha. Now, remember, we need I prime of 0. That is our result. So, we just need to plug in 0 for alpha everywhere. So, I prime of 0 is equal to I, which is then equal to e divided by n squared times gamma prime of 1 over n, right? Yes. Times the incomplete gamma function of n minus 1 over n, comma 1 minus gamma of 1 over n times the Meyer-G function, where m is 3, n is 0, p is 2, and q is 3, and then z is 1. And then we'll have 1 here, comma, 0, comma, 0, and then comma, 1 over n. Okay, so we'll just have a n minus 1 over n. There we go. That is I. I is equal to this ginormous thing right here. Wow. I mean, genuinely, this was a impressive integral, a generalized integral, where, if we recall, n is an element of the positive real numbers. This implies that n is greater than 0. There we go. Now, I hope I made sense everywhere in this video. I hope you had a good time watching this video. Now, technically, this is day 3 of the Advent Calendar Integral Series. Now, leave feedback down below if I made a mistake anywhere, or if I didn't make any sense, or if I was talking too quick, or any type of feedback. And share this video with your friends and family, like and subscribe, and I'll see you in the next video. Have a good day.